Good morning, students. Today we are going to discuss few important topics from chapter 6, that is your electromagnetic induction. Now the first topic which we are going to discuss is your self-inductance of a solenoid. So already we have discussed the magnetic field at the center of a solenoid over its axis in previous chapter. So this is your solenoid, and I is the current flowing through the solenoid and L is the length. Now here we have to define self-inductance, and to define self-inductance, first of all we have to define the magnetic field. So magnetic field already we have defined in our previous chapter, so that expression we are going to use it here. So the magnetic field at P at the center of the solenoid can be defined by the expression number 1, that is B equal to mu naught Ni, and N is your number of turns per unit length. So small n equal to capital N by L. So capital N is your total number of turns and L is the length. Now magnetic flux for one turn or single turn can be defined by this expression phi equal to BA, and A is the area of the turn or area of the loop, you can say. Now if we have to define magnetic field or magnetic flux, not magnetic field, magnetic flux due to the whole length of the solenoid, then what we have to do, we have to consider n turns, that is capital N turns. It means total number of turns. If for a single turn the flux is phi equal to BA, then for n turns it's your phi equal to BA capital N. Now B value is your mu naught Ni, A is already there, area of the loop of the solenoid, and capital N is your small n into L. Now if we simplify, it comes out to be your mu naught N square AL within bracket capital I. Now this is the master equation. Now number 4 equation in case of self-inductance, phi equal to Li. So if we compare 3 and 4, then L comes out to be your mu naught N square AL. So self-inductance of the solenoid is your mu naught N square AL. I think you have understood this one. So this part is very important, and in exam marks is specified on the expression. Statement part you can make and write. I is the current flowing through the solenoid, and P is a point at the center of the solenoid of length L. So this part you can make and write, but the expression part is important. That's why we have given more emphasis on the expression. So let me to show you once again. This is the topic, self-inductance of a solenoid, and these are the expression. Now next topic, we are going to define mutual inductance of a solenoid. Now already we have defined mutual inductance. Now in mutual inductance we have explained that the source is in one coil, that is your primary, but the induced EMF or the change in flux occur in another coil, that is your secondary. So here two solenoid such that they have a common axis. Now we have given number 1 and number 2, solenoid 1 and solenoid 2, and in one current I1 is flowing. So if magnetic field at P we have to define, then we have to define like this. Number 1, B1 equal to mu naught N1 I1. N1 is your capital N1 by L. N1 is the capital N1 is the total number of turns, and small n1 is your number of turns per unit length. Now current is flowing through the solenoid 1, and here we have to define magnetic flux in solenoid 2. So here what we have to do, that is your phi 2, and that magnetic field due to the solenoid 1 is used to define flux due to the solenoid 2, and for that we have to use B1 here. So this should be your B1. Okay, so flux on the solenoid 2 where there is no current, that is your phi 2 equal to B1A. A is the area of each turn. This is for one turn, turn number 1. And for n2 turns, again you have to use this B1, that is your phi 2 equal to B1 A, and here you do have n2 turns, because we are interested in defining the flux on the solenoid 2. That's why you have to use the total number of turns, that is your n2 is the total number of turns. And we have to use the magnetic field due to the current I1. That's why we are using B1 equal to mu naught N1 I1. So N1 you can write capital N1 by L in place of B1, mu naught N1 by L I1, that is your number 1. From number 1 we are getting, and N2 is the total number of turns and A is the area. So if you accumulate the terms, it comes out to be your mu naught N1 N2 by L A into I1. But mutual inductance is defined flux phi 2, that is flux due to the current I1 in the solenoid 1 to the solenoid 2. Current I1 is flowing in solenoid 1, but we are interested in defining the flux in solenoid 2. That's why we have to use phi 2 equal to M I1, and M is your coefficient of mutual inductance. So if you compare 3 and 4, it comes out to be your M equal to mu naught N1 N2 A by L. So N1 is your total number of turns in 1 and N2 is the total number of turns in 2. So in place of N1 you can use this expression N1L, and in place of N2, capital N2, you can use N2L, A divided by L. So if you simplify, it comes out to be your mu naught N1 N2 LL goes off L A. If N1 and N2 equal to N, small n, it means if the total number of turns per unit length is same in both the solenoid, then M comes out to be your mu naught N square A L. So similarly, you can define mutual inductance by considering flux on solenoid 1 due to the current in solenoid 2. So for that we have to use this expression phi 1 equal to M I2, and if you simplify you will get the same expression, that is your M equal to mu naught N1 N2 A L. You can try it in home to take the mutual inductance due to the current through the solenoid 2. We have defined here mutual inductance due to the current in solenoid 1. So you can try, you will get the same expression. Now next topic which we are going to define, all these topics are very important. Energy stored in an inductor. So already you have defined Faraday-Lenz law, E equal to minus L di dt. We are considering the magnitude, E equal to L di dt. Now E is your EMF or potential, so you can write dW by dQ. So work done per unit charge as per the definition of potential. dW equal to E dQ. So in place of E we are writing L di dt dQ. So L dQ dt di. dQ dt is your I, so Li di. So if we have to find the total work done, then we have to integrate considering the limit 0 to I, Li di. So it comes out to be your L I square by 2. So you see the work done in increasing the current flowing through the inductor is stored as magnetic potential energy U. Basically this energy is specified as your U in the magnetic field of the inductor. So you can write it here equal to U. So U equal to Li square by 2. So please go through this topic. These topics are very important, and every frequent year or every year it is used to come. And also let us go for the numerical this part. Calculate the magnitude of induced EMF in a coil of inductance 1 millihenry in which current is changing from 0.1 ampere to 2.1 ampere in 0.01 second. So we are going to use this expression directly, E equal to L di dt. So L is given 1 millihenry, it means 1 into 10 to the minus 3 henry, and change in current is your 2.1 minus 0.1, and change in time is your 0.01. So it comes out here 2 into 10 to the power minus 3 and 10 to the power 2. So 2 into 10 to the power minus 1 volt. So it comes out to be here 0.2 volt. So this is all about. Please go through this topic and try to find out your doubts and put your doubts during class. Thank you.